Hello, everyone. This is Nandita from ECE department, and these are our team members. We have done a course on Coursera called Introduction to Systems Engineering, and yeah, we'll be talking about that one. These are the outline of the topics which we'll be covering in every week, and we have divided the work accordingly. Module 1, Introduction to System Lifecycle. What exactly is systems engineering? System engineering is an approach that involves many professions in a combined effort of designs, implementation, and evaluation. And that's what holds the key to the successful development of the complex human-made system. Yeah. So in week 1, we see that we look into that the very broad places and activities that the systems move through during its life, through what we call the system life cycle, from an early identification by the business of the need of the system, explanation of options and the functions of design of the system, and its physical design, detailed development and construction, production and deployment of the system into service, its utilization throughout its life, its support, and then finally retirement at the end of its life. Systems engineering supports all aspects of life cycle. In this module, some of the key management issues that we came across was systems engineering must address in order to maintain balance and control across the systems engineering effort. We look specifically at issues such as verification and validation, configuration management, technical risk management, and management of technical review and audit program. So what is the definition of a system? In systems engineering, a system can be defined as a set of elements that interact to achieve a stated purpose. It implies that the system comprises of system elements with interconnections and interactions between those elements. And by the very act of identifying the system that we are interested in an external system, boundary is also implied. When we draw the boundary around the selected system elements, we define a system of interest. That system of interest comprises of these system elements and their interconnection that exist within our defined system boundary. The purpose of system is called its mission, which must be clearly stated by business management and stakeholders. So system and its environment. Since we are interested in engineering physical systems that are open, our system interest must accommodate external interfaces. That is, inputs and outputs across the system boundary connected, then external elements that exist in the external operating environment, or perhaps a reloaded system. To extend even further, sometimes we need to be aware of the even wider context. SIO might be considered as a wider part of the operating environment. This is the block diagram of the system and how it's divided. Basically, it's divided into operational products and enabling products. Physical systems that are open, our system of interest must accommodate external interfaces, that is, inputs and outputs across the system boundary, connected to the external elements that exist in the external operating environment, or perhaps a reloaded system. To extend even further, sometimes we need to be aware of the wider context, and the operating environment can be conceived to be a part of a wider environment. In physical sense, we saw earlier that system could be considered to comprise of operational or end product and enabling products. The term system is sometimes considered to be synonymous with products. This is, we say that the product is delivering a system or it's delivering a product. This is the physical hierarchy of a system. We saw earlier that the system can be defined as the combination of system elements which interact to the achieved or a defined mission. Now, since each of these system elements will need to perform functions that will be allocated to it, so as to contribute to a system's mission, we can consider a system to be hierarchical composition of the system elements. In logical description of a system, the system's mission is to break down into hierarchical structure of its major functions. The logical description on architecture, it's also called as functional hierarchy or functional architecture. In physical sense, we saw earlier that a system could be considered to comprise operational end products or enabling products. The end products in the system are also normally described in hierarchy. Here we use simple 4-layer hierarchy. We can say that the top level thing of a system and it comprises of subsystems, each of which comprise number of assemblies, each of which comprise number of components also. And this then forms into physical hierarchy of a system, There are other terms in use, but they are probably most common. The application of these terms to be specific situations and different examples also depend very much on the context of the situation and where within the overall project of the system is being considered. For example, if we take the highest level of aircraft system, we could consider that an aircraft contains, among other things, than an engine subsystem. And then we could comprise assemblies such fuel tanks, pumps and lines, turbines, compressors, gearbox, and hydraulic pumps, and so on. Generic system of a life cycle. Throughout the life of this system, therefore, there are number of phases and activities, each of which builds the results and preceding phase of activity. Now, the sum of these phases and activities is called a system life cycle, which can describe in a model and has 4 broad phases. It starts with the conceptualization of the business needs for the system and pre-acquisition phase. The system is then fine-tuned and formalized and then realized in the acquisition phase. It's then used to and evolved in the utilization phase and finally disposed in the retirement phase. So let's look at each phases of the life cycle. Begins with pre-acquisition phase and with an idea of a system being generated as result of business planning. The early need of the business are confirmed and then supported by business case, which identifies expenditure of organizational resources on the acquisition of the system. In some instances, pre-acquisition phase may determine that it might be not feasible or cost effective to proceed the acquisition. For example, due to technology limitations or funding shortfalls, in the sense, the pre-acquisition phase is where organization spends research and development funds ensure that only feasible cost-effective products are taken forward to acquisition. Once the acquisition phase, once the business needs of the system can be justified, they provide the input of acquisition phase, which is focused on bringing the system into being into service in the organization. This would normally involve defining the system in terms of 3 major artifacts, which will describe shortly: business requirements, stakeholder requirements, and system requirements. We'll also see shortly that the customer could go to develop the system, but most commonly a contractor is engaged to develop a system and then deliver back to the customer, who introduces it into the service in the utilization phase. Utilization phase. The system is operated during utilization phase here, during which the time is also supported by the organization that owns it. During utilization, the system may also undergo the number of modifications and upgrades and different to rectify performance shortfalls, perhaps to meet a changing operational requirement or perhaps because of external environment is changed in some other way, or perhaps even that ongoing support and the system has become expensive and needs to be modified to ease its maintenance. Now the system remains serviced during utilization phase. Perhaps it's being modified over time until the business has no further needs for the system or no longer can do what the organization requires for it to do, or it does, but it's not cost effective to keep in service. The system life cycle therefore concludes with retirement phase. This is like the retirement phase. Here, the system is in service during utilization phase until the business has no further need for the system. It can no longer meet the function required for the organization. It is no longer cost effective to keep it in service. If the business need of the capability still exists in the organization, the conclusion of one system life cycle makes the start of another and process begins again. This is our week 1 certificate that we have completed. Module 2, relevance and benefits of systems engineering. Yeah, system engineering approach has number of advantages also examined in the module. The relevance of the benefits of the systems engineering. The end product through can be considered to comprise of number of subsystems, each of which can be considered to comprise of end product and enabling product. Then each of the products can be considered to comprise of end products and enabling products. This is like the top-down design of a system. Top-down approach, as I mentioned earlier, traditional engineering design methods are based on bottom-up approaches in which the known components are known and trusted to the engineers and design and build. Then they are combined into assemblies and then into subsystems, and from which then the system is constructed. The system is then tested and its delivered properties and design might be modified in an iterative manner until the system meets a design criteria. And this approach is valid. In fact, it's extremely valid and well trusted in engineering. Also, it's very, very useful for relatively straightforward problems and well-defined, such as low-level technical problems, or at least with problems that we have done many times before. Unfortunately, because complicated problems which tend to have a fairly novel phase cannot be solved with bottom-up approach. In systems engineering, we begin by addressing a system as whole, which facilitates an understanding of the system, its environment, and its interfaces before we go about specifying exactly what's inside the system. We start therefore with the system level requirements. Once we understand those systems, it's broken down into subsystems, which are further broken down into assemblies and then into components until a complete understanding of the system is achieved from top to bottom. Top-down approach is very important in managing the development of complicated systems by viewing the system as a whole initially and then progressively breaking down into smaller and smaller elements. The integration of these components can be understood more thoroughly, which then assists in identifying and designing them as a user interface. Those various elements, their internal interfaces, and of course, the interfaces between the system and its environment, the external interfaces, and this top-down approach processes from a system that is decomposed into products and enabling products. All these things need to be done to produce the end products, as we saw this before. Yeah, this is a bottom-up design of the system. Top-down approach is very important in managing the development of complicated systems by viewing the system as wholly initially and then progressively breaking down into smaller and smaller elements. The integration of these components can be understood more thoroughly, which then assists in identifying and designing them as user interface. Those various elements and internal interfaces, of course, then interfaces between the system and external interfaces are also involved. The end product, though, can be considered to comprise of number of subsystems, each of which can be considered to comprise of end product and enabling product. Then each of end products can be considered to comprise of enabling products, and then the prices can continue until the levels of tree can be developed with the leaves of the tree and work packages that need to be done to allow the system to be built. The work packages get allocated to individual terms or individually to actually do, or of course the flip side of the top-down design, integration. We can see here in another representation of top-down design. On the left-hand side of the diagram, the system is decomposed from system into subsystem. Subsystems decompose into assemblies, assemblies decompose into components, and then this is the development. On the right-hand side of the diagram, though, we have flip side of the top-down design, which is the bottom-up integration. Components are built, tested, and then integrated into assemblies. The assemblies are then tested and integrated into subsystems, which are then tested and integrated into final system. The system then finally tested for its design system properties, and so it's completed that the cycle of top-down development and development of integration. This is the relevance of systems engineering. Now, the figure here provides a simplistic illustration of the impact of the systems engineering on the system life cycle. The curve shows that the system engineering is the greatest impact through the rigorous application of the process and methodologies during the early stages of the product, where it's easy to change and it's cheap to modify. In fact, the curve in the figure has been labeled as with the ease which changes and can be made throughout the system life cycle. Now, in the second curve, the figure, the greatest impact of requirement engineering can be seen to come at which when its cost implementing changes is lowest. That is, the earlier we detect and correct errors, the easier they are to correct. Consequently, systems engineering provides the ideal opportunity to have the greatest impact on the project at a time when the changes are easiest and least expensive to make. To make sense of, therefore, the systems engineering leads into reduction of technical risks associated with the system. The risks are identified early and monitored throughout the life cycle. Even earlier on, the process are focused on the feasibility analysis, which chooses the risk to the project. Though systems engineering design decisions can be tracked back to the original user requirements, and conflicting user requirements can be identified and clarified easily, significantly reducing the risk and failure later in the project. Systems engineering framework. In systems engineering process and tasks, which are divided into life cycle stages within they are typically occur. In the course, we don't attempt to detail exhaustively all systems engineering processes. Instead, we concentrate on the intent on main aim of each phase within the system lifecycle and examine some of the likely techniques that may be used to arrive at this aim. Systems engineering management is an overachieving activity responsible for directing the systems engineering effort, monitoring and reporting that effort, and appropriate areas, and reviewing the audit and effort of the critical stages in the entire process. Now, many tools exist to assist systems during the process and management. These tools range from techniques and methods throughout the systems engineering standards. Here, we describe the most popular tools and standards without repeating information that might be contained elsewhere. Now, moving on. This is our week 2 certificate that was done after the quiz was taken. Week 3 and week 4 will be continued by Raksha.
Hello, I'm Raksha from EC. Module 3, Requirement and Needs. Week 3. In week 3, next. In week 3, we understood about the needs and requirements. System requirements are derived from the stakeholder requirements and describes what the system must be based on the requirements. Requirements are generated from needs, though the process of requirement analysis, which are also called basic analysis or a mission analysis at a higher level. Next. The process by which business needs are transferred from the needs into a business requirements is called mission analysis or a business analysis. Once the business managements are satisfied and their needs and the requirements are reasonable completely, the pass them on the business opportunities level. Here, the stakeholder needs and requirements, the SNR definition process with the concept of operations and other PLSs or guidance. Requirement engineers lead stakeholders from the business operational level, though the structured process to the stakeholders' needs and the normal into a form to refine the vision of the concept of operation and the other life system concept documents. Stakeholders' needs are the once again transferred normally into a set of requirements called as stakeholder requirements. Next. At the system level, in the system requirement definition process, the requirements in the STR are transferred by the requirement engineers in the system requirements, which are document and the system requirement satisfied. And of this course, as I said before, requirements can be settled in a various logical grouping that are useful in management. The types can be any types. Some organization insist on having a structural series of type of labels that can be attached. Other allows the system field to be open to allow the people to add any number of types, but the value of the type field is to be able to record after the sort of requirements in this. So it could be safety requirements, security requirements, and train requirements, so on. So in this module, we discussed In this module, we discussed requirements, the level at which they exist, and the relation between at each of those levels. We looked at the number of definition and then finished with the introduction of requirement engineering. In the next module, we are looking more detail at how to create and how to validate the set of requirements. Next. This is a figure of requirement analysis. Requirement analysis is one of the activity of system engineering process and function somewhat as the interface between the internal activities and the external process, providing the input to the process. It examines, evaluates, and transfer the external input into a set of the function and perform requirements that are basics of the functional analysis and allocated. It links with the functional analysis and allocated, and the form of requirement loops and system engineering process. The goal of requirement analysis is determine the needs and make up the system to satisfy all over the needs. The mission and environmental analysis, the customer needs and states them into a terms that can be established system function, perform requirements, and design. The output of the activity functional requirement identification and the design requirement defines the requirement as the activity process. The original assumption and conclusions are checked against, and usually the result is some modification of the normal thinking, and may even refer back to the customer's needs, which are certain, maybe in a circumference of costly. Next. Yeah, this is the certificate of completion of week 3 module. Next. Module 4, needs and requirements and the process of requirement engineering. Next. Yeah, week 4. At the process of developing a good set of requirements, we saw earlier that needs and requirements can be captured in logical or functional hierarchies. Functional hierarchies is produced through two types or two principal process: elicitation and elaboration. Elicited elements are able to directly elaborate the source and normally gathered by the interviewer or the workshop. That means that elicited elements are largely given us directly by the business or stakeholders, or taken directly from some source. Similarly, we were at the low level in design, simulation, module, and prototypes are useful way to understand the legal requirements as well as contain various trade studies and analysis. The entire the process aims to produce a system both verified against the document and produce the system and validated against the original needs and development in the first phase. Next. Yeah. Here are the two principal acts: verification, that ensure that the system at the stages matches the specification have been developed for it and have been built the system right. And then there are validated, which ensure the system meets the original business needs and requirements, that we have built the system in the right way. Now often the two associate aims are combined into a generic terms, and verification and validation are V and V. Return to the diagram shown how the requirement engineering assists in the development of requirements can now work backward. Before the customer accepts the system from the contractor, the delivered system is verified, and it's verified against the system specification. That is we check the contractor as deliver the system to make the things contact them to meet the system specification. Next. So the brief overall requirement management tools. Let's look briefly at the tools that support the requirement engineering, that is the requirement engineering tools. Now here a very large number of such tools that may assist the requirement engineering developing on a particular domain in which they are being done. Here the diagram functional flow diagram, there are the requirements of breakdown structure in the two diagram plus other tools including structural analysis, data flow diagram, controller flow diagram, IDEF diagram, behavior diagram, and many more such diagrams. Each of them tends to be a particular tools used in a particular domain. Here we focus mostly on the time of the two most important tools that requirements breakdown structure, the RBS, and the functional flow diagram, the FFBDS. Next. Yeah, here is an example. The first draft of FFBD for the domain alarm example. The diagram shown an earlier draft, it might have been prepared for the example in a workshop with stakeholders. Note that functions have yet to be formed, written, and the numbering system has yet to be applied. It offers a best to capture the function, inform, and then formalize them. Then it is tried to capture them all in the forms template. Notice that there are very good way of capturing the sensors from which the needs and requirements will be developed. And by simply looking at the diagram, we see what is the users want to do with the system. At the description it is not the RBS which has shown logical relationship. The even PD provides the requirement engineering with the information about the sequential of the function. For example, the residential evacuated after they set an alarm can be seen the first two functional. Alternatively, if you see in the middle of the diagram, all the forms of the entries are equally possible. So the first two functional set the series set are in the series. The entry functions are shown in parallel. That makes a great assistance into a requirement engineering to be able to identify and interface. Next. Yeah, this is a certificate of completion of the week 4 module. Next, it will be overtaken by Bhavana.
Hello all, I'm Priya Bhavana and I'm starting with the module 5 of this course. It is examination of conceptual design. So what is the conceptual design means? Conceptual design is an early stage of a design process in which the board outlines of function and form of something are articulated. So basically it includes the design of interactions, experiences, processes, and strategies. So it is the main thing of conceptual design. Till 4th week, we learned the requirements and different type of requirements and development of requirements. So from week 5, we are doing the conceptual design of the system. So for every organization needs to be successful, and they are in a path to be successful in whatever their endeavors or anything they have to do. They're actively involved in think both operationally, strategically, they have to think. So operational thinking allows them to continue day-to-day or business as usual operations in a smooth, efficient, and effective manner. On large scale, some governments around the country, we know, like plug gaps in government, provide services to the people, health services for disadvantaged people, or transportation services like other military services. So many services will be done by the government. These are all under the larger scales. Next slide, please. So the need to stop our work periodically or check what we are in right place. So we have to know where we are and what we have to do in a faster way. So it is almost too obvious that it goes without mention, but it in the MOOC is an organizer, we'll mention it anyway. So we have done all this work with our business stakeholders. Stakeholders means any organizational managers or something we can call like that, and we think we are ready to move on to solving their business needs. So systems rarely sit in a perfectly isolated situation. Isolated means they are not in a they are not in a perfect situation or something, we can call like that. And it's critical to understand where the system is in irrelevant environment. They are stuck in that, so they have to overcome that problem. So this allows the stakeholders to understand and articulate the scope of the system. By that, they can overcome the problem from the organization. Next slide. We can see here, so this is a establishing a requirements framework. So we are using burglar alarm. We are using this alarm, like this is a type of chart we are using. So in this, we are using deter unauthorized entry, detect entry, classify entry, report unauthorized entry, provide market leading alarm. So these are the types we are used. And in burglar alarm, in detector unauthorized entry, deter in neighborhood, add resistance, system disabling, and detect entry, record entry time, record entry location, detection failure rate. So these are all in the conceptual design only. So mainly conceptual design we can see in this diagram. So first, in conceptual design, the part one is define business needs and requirements. So those are the important things we need to done. And second one is define stakeholder needs and requirements. Stakeholder needs and requirements should be done by their needs. Third one is define system requirements. Fourth one is conduct system level synthesis. We need to know what is to be done and what have to be done to be successful. And conceptual design, last phase is conduct system design preview. So this all gives the preliminary design of the system. Next slide. So this is the certification of module 5 quiz of this course. So coming to the module 6, it is a detailed design decisions. So decisions make a trivial role in the organization or anything. In any organization, one should take decisions like it should be worked to be in a successful way. Next slide. So conceptual design will give the way to get better decisions, and stakeholders can have the idea of what to do, and the capability of business they can improve. And key stakeholders have articulated their understanding of the subsystem level requirements, and in order to explain what the system needs to be able to do, how it needs to be able to do, under what conditions it needs to perform, and what other systems are involved in its performance of those functions. Additionally, the key stakeholders have also decided on how the function and performance of the system will be proven by describing the verification approaches for each of those requirements. Next slide, please. So these are the set of subsystem requirements. We know that subsystem requirements would be allocated to the electrical subsystem. It may be lead to the unknown requirements, such as need to interface the energy company, and we have to maintain the traceability within the requirements hierarchy, and we always know where our requirements have come from. And in system engineering, people only talk about the forward traceability and backward traceability, like to give a feel for which direction within the hierarchy we are talking about. So by ensuring forward traceability exists, we are able to show our stakeholders that we have listened to all of their requirements, and all of their requirements are being accounted for somewhere within our design. So let's use the previous example to illustrate this. If the stakeholders decided that environmental friendliness was no longer required, we'd be able to trace the requirement to the rainwater. harvesting requirements in the plumbing and drain system, like electrical requirements. We can in electrical subsystems, and we will be able to remove those requirements from our consideration. Next slide. So this is the detailed design of the system. Like when we think about what needs to be achieved during detailed design. So it is the main detailed design decision means it is a goal, what we have to achieve in that. So in this, we can see like that business level is this one, yellow mark is business level, and green mark is system level, and these blue marks are all like subsystem levels, and key important role is a detailed decision development. So this will role a this will play a very important role in the conceptual design and system process. Next slide. This is the certification of module 6 in this course.
Yes. So I will be. I was in charge of week 7, which was critical system engineering activities. So, to understand this better, for example, we're constructing our house. We might need to ensure that the earth moving equipment, concrete mixers, pumps, and so on are available when we need them. Specialists also need to be looking after the lead time items that they are a part of our design to ensure these items are ordered in a timely fashion and they are available when needed. For example, in our home design, it doesn't make sense for special equipment like imported tiles or coverings to be late, or it should be in well in advance so that we can continue forward. We may need to store those items in a warehouse or a storage facility in sufficient quantities so that it supports the building. Things like shelf life and storage conditions will then become a consideration. The construction planning will also need to take account of specialized human resource required during the construction. In our example, the list of specialists are long, from equipment operators, concreters, plumbers, gas fitters, carpenters, roofers, electrician, cabinet makers, and so on. These home resources human resources need to be organized to available within appropriate skill and experience at appropriate time. This all takes planning and management. Next slide, please. Yeah. So from a system engineering perspective, the ability to influence the direction that in which the system is taking now rapidly reducing. Making changes at the stage in the process will be very expensive indeed, if possible at all. System engineers are now generally more interested in confirming that the design as specified is in fact being realized. At a major engineering task during the stage is to work towards a system level verification by confirming that the as built system is meeting this specified requirements. We can do this in a varieties of way, but generally a combination of inspection, analysis, tests, and demonstration. Let's look at some examples. Inspection. We might need to verify that the given layout requirement has been met in our kitchen. We would simply inspect the kitchen to confirm this analysis. You need to verify that the electrical system was able to safely interface with the main power. We would want to confirm that the installed switchboard has been previously approved for this sort of task. We may do this by analyzing the documentation and the certificates that come with the switchboard in our electrical system. Next, please. Yes. So there are generally two type of audits conducted by system engineers: functional audits and physical audits. Configuration audits makes heavy use of verification results discussed previously to confirm that the system functionality is accurately reflected in the system's documentation. By completing the functional configuration audit, we can be confident with our documentation accurately describes the function and the performance levels of our system. A system configuration audit confirms that the physical description of the system is consistent with as built item. This ensures that there are certain things like materials, parts have been used in the construction and layout of things like interface and the critical points to note, especially that within physical audits, is that they can often be done during construction production and not after. For example, physical audit of our house will be able to confirm that the drawings of things like stormwater sewage connection is accurate on the drawings. Next slide, please. So the only way to do this is to walk around the block and to confirm that the location of pipes in the ground are is as per drawing. This needs to be done when trenches are still open and the inspector can see the pipes on the ground. The inspector is then able to correlate what he sees on the ground and then he or she sees in the drawing. For example, uh, next slide, previous slide, please. Previous slide. Yeah. So from this drawings, yeah. So let's say one of the example given in the course was where the instructor told that he needed to locate the stormwater drain so that he could finalize an irrigation system in his garden. If he was not certain of the exactly where the storm water pipe was, he would have to dig around the garden until it was found. This digging would damage the established garden and potentially cost a great deal of money to be repaired. Fortunately, when the house was being constructed, he walked around with the plumber and the drawings and confirmed exactly where the pipes were laid. So the need to perform certain audits on a system as it passes through production and construction phases. And one more important audit is physical configuration audit or PCM. Next slide, please. Yeah. So to explain what PCA is looking for is to confirm and it why it's performed during construction and production rather than before and after production. So PCA is essentially looking for confirmation that the as-built item and the item's technical documentations are aligned. It is we are looking to ensure what we see is what the technical document says that we are going to get. In the course material, we saw like the example of ensuring consistency in between drawing of showing a location of the stormwater drain, the actual location of the drain in the ground. This allowed us to locate the drain. Later, the instructor was able to carry out changes to the watering system in his garden. It sounds obvious that we it sounds obvious, but the build states need to be checked. If we don't do this, it won't be 100% sure as as the drawings and the material list and the layer drawings will reflect in what is built. Some people will say that it doesn't really matter. A few errors in the drawings will work as long as the system works. But these people should realize that they come across these problems later in the system life during utilization phase where we cannot maintain, upgrade or modify the system because of technical data is incorrect. So this needs to be done during the production and construction phase. It cannot be done before, because the system elements that we were auditing it will not be in place before construction and production. PCA cannot be done after construction and production, because a great deal of what we are trying to check will be hidden from us by that time the system production and construction is complete. For example, we saw this in the given example of the drainage pipes. Next slide, please. So this is my week 7 certificate. Week 8. So the need for testing the system prior to its use is self-evident, but what sometimes is not clear is the time, money, risk associated with the comprehensive test programs. Unless it is managed properly, the waste will occur and testing program will fail to deliver the expected results. Managing the configuration of all elements of our system can be tedious, but if not done properly, it will sentence throughout this life support of stakeholders to pain and frustration as they attempt to support our system whose configuration is not known. Imagine trying to modify a complex system when the system does not appear to be accurately documented, or it seems to be insignificant variation configuration across a fleet of systems that are meant to be identical. Risks is essentially the chance of something happening that adversely in fact impacts on adjectives. On a technical system development, there are plenty of risks that we face routinely. Next slide, please. Next slide, please. Next slide, please. Yeah. So first, we'll see waterfall approach or waterfall method. So this is a classic process which our instructor told, and he explained in great detail. We'll see it in a short. Okay. Sometimes as waterfall approach, we choose this approach for this course for a bunch of reasons. Firstly, it remains popular approach to system engineering. Secondly, it is logical and sequential, making it ideal for explaining the whole system engineering process. Thirdly, even if it is not used as development approach, it still represents basic building blocks of other popular approaches. So, for example, when we have enough time and money to do a lot at once, we understand the requirements of system well and enough to base the whole effort on the requirements. When the requirements are sufficiently stable that they don't keep changing, when we are forcing expensive and time consuming rework, at when system technology and expertise and sufficiently available and stable to be able to solve the whole problem at once. Note, these to be successful, pretty much all of these things need to be in place. These are the conditions of the waterfall approach to work. So what waterfall approach is essentially going step by step. So first we see the requirements of our stakeholders and other people involved, design and how we're going to implement the system, testing and maintenance. So essentially we're going to start from system and we're going to go down till the subsystem levels. Previous slide, please. Previous slide. Okay. Testing. Why do we test or evaluate things? We need to verify that our design and development effort has been successful by confirming our design has resulted in components, then subsystems, and eventually a system that has made specified requirements. This helps in identify areas where redesign might be necessary. For short, verification is sometimes called development tests and evaluation. For example, the component testing might be to test different types of concrete before deciding what type of concrete to be used. We would then test the concrete as it's arrive on pure side to it being poured onto evacuations. Although it would appear to be inconvenient and might affect a few people, this should be by a series of demonstration, inspections, and tests, to use the term we came before. Once the system enters the utilization phase, we continue to evaluate the system. Generally, this sort of evaluation aims to continually validate that the system is solving the problems that created and is in need in the first place. Naturally, this sort of excessive exercise involves the system being employed in operational environment, being used by the end user, and who are trained by a training system supported by a support system, and so on. Validation. Next slide, please. Validation occurs when we take steps to confirm that the system achieves the purpose or the need that the kick of the whole process off in the first place. As we go through the system engineering process, we should always keep in validation in mind. For example, we might think the system specification is good enough from requirement perspective. We might need to make sure it is in fact going to the result of the system meets our stakeholder needs. This process continues down the system requirements hierarchy. Naturally, when our system rolls out of production and construction process and into operational service, we will be able to confirm or validate what we've got is all right. At this point, we'll combine our system with our people, our support environment, and so on. We'll be using our training system, we'll be interacting with external system, and it all adds up to a satisfied stakeholders. Then our system is bound to be validated. If not, we got a problem. That's why we gotta go through system engineering levels. We must continuously look back to make sure we are not doing only the job right, but also doing the right job. Verifying and validating the system this way is a risk mitigator, because it allows us to confirm the system design adequacy, detect problems early, and confirm rectification action, and so on. In other words, it helps us from ending up with a system that doesn't work in a way intended to work. And also, the course instructor also recommended us that to correct the problems as soon as they pop up and to detect regularly. Next slide, please. Next slide, please. Yeah, disposal. Previous slide, please. Disposal of a system is becoming very important these days. Why? Because the concept of environmental responsibility is taking on much more significance as we move through the 21st century. What was acceptable yesterday will be no longer acceptable tomorrow. We can no longer afford to throw things away without due concern for the environment and the future. As system engineers, it is our responsibility to try our best to ensure that the disposability drives our system and development. So we may end up with a system that in fact be disposed in a responsible and in a cost effective way. Next slide, please. This is my certification of the 8th week. Next slide, please. Thank you.
Thank you.
Thank you.
Thank you.